Good morning. Welcome all for another session on cryptography, network security, and cyber law. Today we will continue our discussion on Module 3. And in today's session, we'll be discussing about identity based encryption. And also, we will start off with the introduction to authentication. Now, the agenda of today's talk includes, as we already told, identity based encryption, and wherein we will be using the client's ID in order to get the public private key pair and use it for performing encryption and decryption. Along with that, we will see how keys are generated. Now, in order to perform this identity based encryption, we have to build upon certain preliminaries, and also we need to understand what we mean by bilinear mapping and bilinear pairings, and also we'll see how bilinear pairings are used to achieve this particular identity based encryption. And moving further, we will in the second half of the session we'll be discussing on one-way authentication. We will see how this one-way authentication is classified, and will also authentication is classified. We'll see first how authentication is classified, and within this we will see the classification of one-way authentication. Now over here we have specified that in one-way authentication we have password based authentication and certificate based authentication. Now these two topics will be discussed in subsequent session. All that we'll do in today's session is introduce you to the concept of authentication and what we mean by one-way authentication. Now the objectives of today's session would be that you'll be able to explain the various concepts involved in bilinear mapping, bilinear pairing, and also you will be able to explain identity based encryption based on bilinear pairing. Followed by that, you'll be able to describe what is meant by authentication, especially one-way authentication. Now let's get on with what we mean by identity based encryption. Over here we'll discuss two particular topics. One is preliminaries, the bit of mathematical concepts which are used to build upon this particular encryption technique, and also the second topic, that is use of bilinear pairings, will tell us how to use these bilinear pairings in order to achieve identity based encryption. So moving further, we will start off with preliminaries. Let me get rid of this. Okay. Now in identity based encryption, we have seen that previously why digital certificates are used. Digital certificates is a best way to send a public key to the subject, and the public key that is sent to the subject is easily verifiable because digital certificate securely transmits that particular public key. Now these certificates can be transmitted either along with the message that is sent for authentication, or it could be for signature verification or encryption. Now, this digital certificate concept was overcome, or an alternative to this was proposed by Shamir. Shamir is one of the fames that proposed the RSA algorithm. Now he proposed another encryption technique called as identity based encryption. Now in this topic, in these subsequent slides, we will be discussing about identity based encryption. Now in this Shamir's identity based encryption scheme, let's say Alice wants Alice wants a public key. Now Alice public key can be computed by the certificate authority or any centralized authority, but just by Alice providing her email ID. Now over here Alice is just providing her email ID. A function of this email ID, which is unique, is calculated, and that calculation will provide Alice with the public key. Now Hence, anyone who is having Alice email ID will be able to get the email ID. Will be able to get the public key of Alice. Now, this identity-based encryption was based on the RSA algorithm. Because it was developed by Shamir, he used RSA in order to propose this particular identity-based encryption. Now, in 2001, Bonnet, another computer scientist, used bilinear pairing in order to perform this identity-based encryption. Now, to understand what we mean by bilinear pairing, we will just discuss henceforth. Now, let us see what are the assumptions made by Bonnet for identity-based encryption using bilinear pairing. Now, this identity-based encryption uses a trusted third party, which is called as TTP. Now, this TTP, or the trusted third party, is also called as private key generator or PKG. Okay, trusted third party and private key generator, both these terminologies mean the same. Now, this trusted third party is responsible for providing the user with the private key. Now, let's see how this works. Now, the step 1 over here is the private key generator, or the PKG, has the private key and public key parameters. Now, the PKG's private key is kept private to PKG itself, whereas the public key parameters of this key generator is made publicly available. Now, in the second step, what is happening is Alice is a client who is requesting the private key generator for a private key. Now, there is a communication occurring between Alice, from Alice up to the private key generator. Now, over here we can see that for the second step, Alice is making a request to the private key generator. Now, for making this request, Alice is asking PKG to generate a private key for Alice. Now, for that, Alice is sending her email ID. Okay, let's see what happens in the first step. In the first step, it occurs entirely at the private key generator. The first step is entirely occurring at the private key generator. Okay, entirely at the private key generator. Whereas wherein PKG has a private key generator is generating its private key and the public key parameters are made known to the public, whereas the private key is kept private to the public key generator itself. And the second step happens between two communicating entities. One is the Alice and the other one is the public key generator. Over here, Alice is asking the public key generator to generate a private key, and in order to generate this private key, Alice is providing her email ID. Okay, now let's see what happens in the step 3. Now, the step 3, PKG, that is the private key generator, will receive the details, that is the ID, from Alice. Now, PKG processes these details received from Alice. And what does it do in the processing? It first checks whether the email ID that is provided by Alice actually belongs to Alice. Now, once that is checked, it also checks if this ID which is provided by Alice is unique. Also, moving further, after these two checks, if they satisfy, then the private key generator generates the private key. Now, how is this private key generated for Alice? The private key generated for Alice is a function of Alice email ID along with the private key of the private key generator. So, it is not just the function of Alice email ID. It also is a function of the private key generator of generator's private key. Okay. So, Alice email ID along with the private key of the private key generator will be set subjected to some function which will provide us with a private key of Alice. Now Alice private key is generated by PKG. Now once this private key is generated, the PKG securely transmits this to Alice. Now this private key that is transmitted to Alice will be received by Alice and used for further communications. Now note that the knowledge of Alice unique ID and the PKG public parameter, these are all public parameters, right? Email ID is known to everyone, and also the public key generators public parameters are known to anyone. With these two information, anybody is able to compute Alice public key. And also Alice public key is a function of Alice email ID that is unique to Alice, and also PKG's public parameters. So now over here we can see that how we get the public key of Alice. Now the entire process says that the first step is wherein the public key generator will generate his public private key pair. This private key is kept private to public key generator, whereas the public key is made known to public. Now what happens in the second step is the client is making a request to the public key generator for its private key. Now what does the client do for this? She's sending her email ID requesting for a private key, and then once this is received by the public key generator checks for the uniqueness and also whether it is actually belonging to Alice. If both these checks are cleared, then the public key generator will generate private key of Alice. Now this private key is a function of what? Alice email ID and the private key of the public key generator. Now what happens in the fourth step is once the private key is generated by the public key generator, it has to be securely transmitted to Alice. Now after receiving the private key, the Alice is able to perform various services that are required, either confidentiality or whatever. Now how does the other party get to know Alice public key? Now in order for the other party to know Alice public key, they just need Alice unique ID and the PKGs, that is the public key generator, private key generators public parameters. Now these two are made public or they are publicly available. Now using these two values or using the knowledge of these two, anybody can compute Alice public key. Hence Alice public key is a function of Alice unique ID and also it is a function of private key generators public parameters. Now let us see how we use bilinear pairings in order to achieve identity based encryption. Now we will see few of the basics and then we'll see its actual implementation. Now let's try to understand what is bilinear pairing. The bilinear pairing B of xy, it is represented as B and B of x and y. Now over here this pairing maps any pair of elements from given one set to any element in the second set. Okay, elements from one set are mapped to elements of another set. Now this bilinear pairing will have the property of k1 into u1 plus k2 into u2 and v is equal to k1 into bilinear pairing of u1 and v plus k2 into bilinear pairing of u2 and v. Now over here u1, u2 and v are the elements of the first set, whereas k1 and k2 are integers. We will see how this works. First we will try to prove this and then prove this, or either way. Now let's take an example of bilinear pairing. For that first let's see what we mean by dot product of two vectors. Over here we have two vectors u and v. U is having three elements 2, 4 and 1. V is having 5, 3 and 2. Now the dot product of u and v will be 2, 4, 1 dot product 5, 3, 2 transpose of this, which will give us 24. So this is 2 5s are 10, 4 3s are 12, plus 2 1s are 2. So 10 plus 12 plus 2 will give us 24. Now this is how dot product is calculated. Now let's see how dot product of bilinear operations is performed. Now we have U1, which is having 3 elements 2, 4 and 5, and U2 is having 7, 1 and 2. K1 is having a value of 3 and K2 is having a value of 4. Now what's happening over here is we are trying to perform this operation of K1U1 plus K2U2. Now K1U1 and plus K2U2 is equal to, K1 is 3. Over here it is given that K1 is 3 and K2 is 4. 3 into U1. U1 has elements 2, 4 and 5. So 3, and we are using this 3 to multiply all these 3 elements. And K2 is 4 and U2 is 7, 1 and 2. It's given here. Now we will find the product of 3 into this particular U1 vector. 3 into 2 will give us 6, 3 into 4 12 and 3 into 5 is giving us 15. Similarly, after performing this multiplication we get 28, 4 and 8. Now these two vectors are combined together in order to get 34, 16 and then 23. Now this is what we have got for the LHS K1U1 plus K2U2. Moving further, we need to find out into V. Now we have seen how to find the dot product. 34, 16 and 23 is what we have obtained through our previous step by finding K1U1 plus K2U2. Now dot product along with V will give, what is the value of V? We have V over here, it is 5, 3 and 2. Now a transpose of this 5, 3 and 2 is multiplied to the previous vector in order to get 264. This is 34 into 5 plus 16 into 3 plus 23 into 2, which will give us 264. Now over here I have specified how this dot product is calculated for this particular, these two vectors. Now the outcome of this is 264. Now that we have the value, we have seen B of this LHS, the bilinear mapping at this left hand side is 264. Now let us see whether the same value is obtained by calculating the values on the RHS. Now at the RHS we have seen that it is K1 into bilinear mapping of U1 and V and K2 into B of U2 and V. Now first let us see by substituting the values. We know K1 is 3 and U1 is 2, 4 and 5 and V is 5, 3 and 2. First we will perform the dot product of these two, through which we will obtain 32, and similarly K2 is 4 and U2 is 7, 1 and 2 and V is 5, 3, 2. We are applying it in transpose. So the outcome of this dot product is 42. Now 3 into 32 plus 4 into 42 will give us 246. Over here we are able to prove that the LHS is equal to RHS. Now this is what happens in case of bilinear mapping. Now the same concept has been used in order to achieve identity based encryption. Now let us see how this bilinear pairing can be used to achieve identity based encryption. Let me remove this. Okay. Let's see how this bilinear pairing is used. Let's say there are two groups G and GT. G is the regular group and GT is the target group. Now over here these two cyclic groups are order of prime number P. The bilinear pairing B of XY maps pair of element in a group G to that of GT. The element in the group is mapped to the element in the target group with the help of bilinear mapping. This is what we are trying to specify through the second point. Okay, the element in the group G is mapped to a target group element with the help of bilinear mapping. Okay, over here two elements are mapped to an element in a target group. Now let's see further requirements. G is an additive group with an identity of 0 of G, whereas the target group GT is a multiplicative group with identity 1G. Now what are the various properties of bilinear mapping? Now bilinearity is for all the elements x, y and z which belong to the group G, they have to satisfy these two conditions. Wherein bilinear mapping of these for the elements x plus z and y is equal to bilinear mapping of x comma y into bilinear mapping of z and y. Similarly for the other condition. Now let's see what we mean by non-degeneracy. Now for a given x element which belongs to group G, the bilinear mapping is equal to 1G. And for all y which belongs to the group G, it belongs to this particular group if and only if x is equal to 0 of G. That is, it is an identity element for an additive group. Now what we mean by ease of compatibility. Now ease of compatibility refers to the fact that there exists efficient algorithms which can be used for computing bilinear mapping among pair of elements for all these elements x and y such that they belong to the group G. Now using these three features, let's see what happens in case of identity based encryption. Now over here, once the groups G and GT along with that bilinear pairing B are decided, the groups and the bilinear pairing B, all these three parameters are decided, and also PKG will proceed with setting up of its own public key parameters. Now these public key parameters will be made public because it will be used to calculate the client's public key along with the ID of the client for which the public key has to be calculated. Now once the public key generator proceeds with generating its public key parameters, the client may then request for a generation of her own private key. Now let's see how this exactly works. First, let's start with the discussion of public key parameter setup. For that, the public key generator has to choose generator P. P is a prime number which belongs to the group G. Moreover, it also chooses a random number K. Now this random number is used to generate the public key of the PKG. Now over here we have this random number which is a private key of PKG which is multiplied along with the generator P in order to get the value of public key of PKG which is represented using a capital K. Also, the public key generator chooses two hash functions I and move. Now what does this first hash function refer to? The hash function I maps the person's ID. This person's ID is of arbitrary length and this ID is usually represented in binary. Now this hash maps the person's ID to an element in the group G. Now the question that arises is, what does mu do? Mu maps an element in the target group to an L bit string. Now what is this L bit string? L is the length of the message block. Now this is what happens at the private key generator, and this is the initial step that happens even before encryption and decryption. Now this is step 1 according to our algorithm that we discussed initially. Now let's see what happens further. Now the information that is known to the public is the two groups information, that is G and GT, the generator P. Now this is generator P, and also the public key of the public key generator K. This generator P is a prime number, then public key of the generator K, and bilinear mapping B, and two hash functions I and mu. All these information is known publicly. Now let's see what happens further. Now using this information, public key generator has to generate the public key. How does it generate the public key? Let's try to understand these steps. According to the second step of the algorithm, we have seen that the client A is the client who requests PKG for the private key. Okay. Now during this request, what does the client do? The client will send, that the client over here is A, it will send its email ID. Now let's call this email ID as ID of A. Okay, till here I hope this is clear. This is the second step. What is happening? Alice is requesting for the private key generator for generation of private key of Alice by sending its own email ID, which is represented using ID A. Now the private key generator performs various checks. What were those checks? First is that this particular ID which is supplied by A is actually belonging to A, and also that this ID which is supplied by A or given by A is unique in nature. Once these two conditions are satisfied, PKG proceeds further with the private key generation of Alice. Now let's see how this happens. Now over here, the ID of A, that is Alice, is taken along with I. I stands for hash over here, along with the I hash, and computes the public key of A. Now this public key A along with the key of the PKG, this key K is what? It is the private key of public key generator PKG. Okay, private key generator along with the public key of A will give us private key of A, that is represented as alpha. Now the work of PKG after calculating the public private key pair for A is to securely communicate this particular alpha and the public key to A, that is Alice. Now having understood the first and the second step, we will see how encryption is actually performed. Now suppose that Bob wishes to send a message to the client Alice. Now what does Bob do? Bob has to request for the parameter from public key generator. It has to request a public parameter of the public key generator if it does not have one. And also Bob needs to know the email ID or the ID of the client A. Now using these two information, that is the public key parameter of the public key generator and also the client Alice email ID, he can calculate and encrypt the message and send it to Alice. Now how does this happen? For this, let's say M is the message that needs to be communicated. Let's say M is a message that Bob wishes to send to Alice in an encrypted form, and this M is of length L bits. Okay, this is of L bits. Now, B chooses a random number. Bob is choosing a random number R. Now, using this, Bob will compute C1 and C2. C1 and C2 are the ciphertext which we will compute. Now, over here, R is the random number chosen by Bob. Along with that, he will use the generator P, which is the prime number P, in order to compute C1. Now, he will compute the actual ciphertext C2 over the message M, which is XORed with the second hash and the bilinear mapping of A. A is Alice public key and R of RK. Okay, R is the random number that is chosen by Bob. Along with that, key K is used. Now over here, this pair C1 and C2 both are communicated to Alice. On receiving this, Alice should be able to decrypt the entire message and get back the message M. Let us see this process. So for this, Alice will use her private key alpha, and also we need to get back what? The message M from ciphertext C1 and C2. C1 and C2 are sent by Bob to Alice. Now what is happening here in the first equation? C2 XORed with mu B, and alpha is used in order to retrieve the message M. Along with that, we use C1. Now let's see what alpha refers to. Alpha refers to Ka. Now we will replace this alpha with that of Ka, and then C1 is obtained by Rp. Now we'll replace this with R and P. Now over here, C2, now this entire information can be rearranged. A can, over here we have seen that moving these values in the bilinear pairing will not affect much. A, this we call it as bilinear property. So over here, K is moved here. K into P will give us capital K. Now what is this capital K? Capital K is public key generator's public key, which is known to everyone. Now using this particular equation, wherein Alice is having access to C2 because it is received from Bob, XOR it with the hash which is made public, that is mu, and bilinear mapping B of A and RK. Now this RK, K is what? K is public key generator's public key, and A is Alice public key. Now Alice public key is known to us. We know the value of K. Easily we will be able to, Alice will be able to compute and get back the original message M. Now over here, this is the various steps that are involved in the calculation of keys, and also how we perform encryption and decryption using bilinear pairing in identity based encryption. So other known bilinear mappings will include Weil and Tate pairings. Now these details are not in the scope of your syllabus. Now let's move further with the next topic, for the second half of this session, which is which is authentication. Within this, we will discuss about what we mean by one-way authentication. Now, authentication is a process in which we are trying to prove the genuinity of a source and the message. Now, over here, authentication is defined as a process in which the principal proves that it is the entity that it claims to be. The person who proves himself is called as the prover, and the party to whom this prover is proving is called as the verifier. The verifier should be able to get to know that the prover is authentic. Now, authentication based on what principle knows or has is it can make use of a password or a passphrase or an identity, or it could make use of an passport to prove its authenticity. Usually what we do is we use ID card in order to prove our authenticity if we are physically proving ourselves, or if we are trying to prove to either our computer system, or it could be up to a particular application, we use our password or a passphrase. Now, if the person who is proving is a human or a computer or an application or a robot, let's see what happens. Now, if the person is a human, in that case he can use his voice to prove his authenticity, or he can use a fingerprint to prove his authenticity, or a retinal scan to prove his authenticity, or a DNA sample. Now, any of these forms of authentication, we refer to them as biometric authentication. Now, what do we mean by password based authentication? Now, over here, an individual communicates his password to verifying authenticity, but it is exactly not apt to reveal your password to anybody. Now, instead, you can use some sort of one-way cryptographic operation to prove the authenticity. Now, when these authentication techniques are used, we call them as multi-factor authentication. Now, let's look at the classification of authentication. Now, over here we know that in authentication, a particular person or a source is trying to prove his genuinity to a receiver. Now, there are two ways in which it can be performed. One is one-way authentication and the other one is mutual authentication. Over here, only the source is trying to prove himself to the receiver. Over here, both the source and the receiver has to prove their authenticity to each other. So, over here, in case of one-way authentication, we have two types. First is password based authentication and the other one is based on certificates. And in case of mutual authentication, the first method is making use of a shared secret key, and the second one is based on asymmetric key, and the third one is based on key agreement. Now, let's see what we mean by one-way authentication. Within this, let's look at the classification involved. Now, in case of client-server communications that occur in a network, be it a campus network or any network, it is often that the client has to authenticate himself or itself to the server. Now, over here, even in case of an email application, when we open our Gmail, we as clients prove ourselves to the Gmail server. Now, the server, if you provide an appropriate password, it will retrieve back with your Gmail box or with your email box. Otherwise, you will not be authenticated to use that particular Gmail box. The server may or may not be authenticated to the client. Now, the Gmail server is not proving its authenticity to the client, but whereas as a client, you are proving yourself to the Gmail server. Now, this process is referred to as one-way authentication. There are two ways in which you can achieve one-way authentication. One, we call it as password-based authentication, and the other one is certificate-based authentication. Now this password based authentication and the certificate based authentication we will be discussing in our next session. Now let's see what we have discussed in this entire session. Now over here in this entire session we started our discussion with bilinear pairing, which is used for identity based encryption. We have seen that identity based encryption is an alternate method for using digital signatures. Now the digital signatures were actually used to communicate public key of a client, and it was a verifiable way to communicate the public key of a client. Now this identity based encryption is able to provide a client with its public private key pair, and that too in an efficient manner. Now for this we have used bilinear pairing. Now the person who introduced this concept of identity based encryption, that is Shamir, used the concept of RSA. Now Bonnet expanded or extended this version of identity based encryption using bilinear pairing. We have seen a simple example of what we mean by bilinear mapping, wherein elements of one group are mapped to elements of another group. We have mathematically proved how this mapping is true. Then we have seen the various properties involved in bilinear pairing. Followed by that, we have seen the four steps involved in the identity based encryption algorithm. The first step is wherein the public key generator was setting its own public parameters, and the second step was wherein the client Alice was making a request for a private key to public key generator, and also the third step was wherein the public key generator, that is PKG, is verifying the credentials of Alice, and then if the credentials were true, it was going ahead with the generation of private key of Alice. Now the fourth step was securely communicating the keys generated for Alice to Alice itself. Now having the knowledge of public key generators, public parameters, and Alice email ID or the ID of Alice, any other client within the network was able to calculate the public key of Alice. Now this is the entire algorithm that we have discussed. Now moving on, we have discussed about one-way authentication, and we have seen what exactly we mean by authentication, what is one-way authentication, what is mutual authentication, and that there are two categories involved in one-way authentication, which is password-based authentication, and the other one is certificate-based authentication. So these two concepts, and along with many other concepts of mutual authentication, we will be discussing in session 4. Thank you. If in case you have any queries related to this particular session, you can just refer to this session number and the module. Along with that, you can just drop in an email, or you could ping me on this particular number. Thank you.